In this video, we are going to see the most important property of a signal while doing an operation, and that is called as a convolution. We will explain this concept with the help of discrete time, where the convolution is called as a convolution sum. In the background, we can see there are two most important properties of any system, and that is a linearity and time invariance. So in practice, we do have systems which are LTI, stands for linear time invariant system, where one important thing, that is a convolution, we can perform on LTI systems. So let's discuss about the convolution. Before going for a convolution, I would like to have one simple discrete time sequence x of n. Let's represent it like this. So from minus infinity, it is started and maybe having a value 1, minus 2, then 1, minus 1, 2, and it can go up to infinity. A random sequence I have taken with origin at this point. So if I plot this, it will be like this. From minus infinity it has started and it is going to plus infinity, and on this n axis it is n equal to 0, n equal to 1, n equal to 2, like that. And in negative axis it's minus 1, minus 2. So if I plot, I will get a sequence like this. For origin, it having a value 1, for n equal to 1, it is minus 1, for n equal to 2, it is plus 2, for n equal to minus 1, it is minus 2, and for n equal to minus 2, it is 1, like this. So just a random time sequence in discrete time we have taken. So what it states, every element in x of n can be represented in its impulse function delta. Let's see how. So first let me define the delta function. So delta function is represented as a delta n, and it exists only at n equal to 0 and the magnitude is 1. For rest of the instance, it will have the value 0, like this. So it's a delta function, and this delta I can shift, that means I can delay, I can advance. So let's consider this delta is delayed by 1. So it will have the magnitude equal to 1 at the instant 1, and I can call this as a delta n minus 1. Similarly, I can advance this to make delta n plus 1. So it will have the magnitude 1 for n equal to -1. So the magic of this delta is that whenever I multiply delta with some function, I will get only a value present equal to the original sequence, but the instant is decided by delta function. Meaning, if I want to have the value of x of n and I need to just display what is the value at n equal to 0, I will multiply this entire signal with delta n so that it will make the remaining part 0. Only thing is that whatever value present at n equal to 0 for x of n will be displayed. In the end, what I can say, any sequence x of n can be represented as a shifted version of impulse functions. Meaning, let's take this example where I need to know what is the value at n equal to -2 for x of n. So what I will do, I will simply multiply this x of n with delta n plus 2. So I will get a value present only at n equal to -2, and that is equal to 1, which I can write like this. It is x of -2 multiplied by delta n plus 2. Meaning I advance the delta function by 2 units so that it will make the rest of the values beside n equal to -2 as 0. So I can say x of -2 multiplied by delta n plus 2 is like this. Same way I can have the value for n equal to -1 for x of n, which is -2. So it is like this. And the expression is x of -1 delta n plus 1. Let's go ahead and find out the value x of 0. So x of 0 is 1. I can write this as x of 0 into delta n. Let's go in the positive side where the values are -1 and 2 for n equal to 1 and 2 respectively. So I can say I will get like this, which is x of 1 multiplied by delta n minus 1, and in the end for n equal to 2 the value is 2. I can write it as x of 2 multiplied by delta n minus 2, so on and so forth. So what I'll do, if I add all this, I will get a x of n sequence. So I can say x of n is, it is continuing from -infinity plus x of -2 into delta n plus 2 plus x of -1 delta n plus 1 plus x of 0 delta n plus x of 1 delta n minus 1 and x of 2 multiplied by delta n minus 2, and it can continue. So what I have done, I have written original sequence x of n as a linear combinations of shifted delta from say minus 2 to 2. So shift is from minus 2 to 2. Now what we are going to do with this is we are going to consider this as an individual sequence which is applied to the system whose impulse response is known to us. Okay, so in order to understand this, we will take one simple problem. So in the problem, I will have x of n, a sequence having the values 1, 2 and minus 1, and somewhere here is the origin. So x of n is like this. This x of n I can write in terms of delta, so let's write that delta first. So what we'll obtain is this. I'm getting a signal having the value 1 at the instant minus 1, which is nothing but x of minus 1 into delta n plus 1. So how I will remember this? I will consider this is a signal which is a shifted delta by 1 in left hand side. That means it is advance with a magnitude x of minus 1. Similarly, second signal I'll get at n equal to 0. The magnitude is 2. I can say this is x of 0 multiplied by delta n. So once again I will consider this as a delta n function with a magnitude decided by x of 0. And finally, I will get a value at n equal to 1, which is nothing but minus 1. I can say this is x of 1, which delta n minus 1 need to be multiplied. So I can say this is also a delta function, which is nothing but shifting delta n by 1 in right hand side, means it's a delay with a magnitude decided by x of 1. Now what we are going to do, since we know what is the impulse response of a system, now let me consider impulse response. Impulse response of a system means to a system obviously we need to consider it as a linear time invariant system only. if I give the input signal as a impulse, the response I'm getting is represented by this. So impulse means it is a signal exists only for n equal to 0 with a value 1, and corresponding output I am getting as h of n. So we'll do one thing, we'll consider a random impulse response for this particular LTI system which we are going to apply for this. So let's consider the impulse response of a system is so I'm randomly selecting that if the impulse is applied to the system, I'm getting an output as, let's consider it is like this. One, and -1. So interval from -1, 0 and 1. So this is a delta n impulse function applied to the system. Obviously it has to be a linear time invariant system, and this is h of n. Since this is given to the linear time invariant system, now we need to check for a shifted and a scaled impulse how the response we are obtaining. Meaning, suppose now the signal is like this, delta n plus 1 and the magnitude is x of -1. As per the property of a linear and time invariance, now I need to check what will be the response we will get. So what I said now, suppose I'm having a signal like this, which is a scaled version of delta n by say amount a, then I will call this as a delta n. If I pass through this system which is linear time invariant, I should get a corresponding magnitude multiplied with a capital A. So we should get a response like this. For the instant -1, 0, 1 respectively, which we call as capital A times h of n. Similarly, if I shift this, so a delta n, this I'm getting because of the linearity property. What linearity property says? It should fulfill the condition of a homogeneity or scaling as well as superposition. There is no question of having a superposition right now. It is just a scaling property it is fulfilling. Now suppose this signal is shifted by some amount k. So I will get an instant like this. Somewhere here it is 0 and it has shifted by k. So this signal is having a magnitude a shifted by k. So it is a delta n minus k. Once again, if this is passed through the linear time invariant system, what we should get? The impulse response that we obtain should also be shifted by k unit right side. So we should get the expression like this, where the k shift we can have any random number, but the signal that we obtain will have the nature like this. and since I'm shifting this side by k amount, so this is -1 minus k, this should be minus k, and this should be 1 minus k. So what we are getting over here, a shifted version of the input signal result into same shift at the output signal. So this is a property of a time invariant. Now let's apply this property to our signal, which we have taken like this. So we'll find out now one by one how we are getting. So now I will have the signal with a magnitude 1, but basically it is x of -1, and it is advanced by 1 unit. This is given to the LTI system. Now we need to check how the resultant impulse response will change. So this is the impulse response we are having. Now what we need to do, this need to scaled by the amount x of -1, which is 1 in this case. So I can say I will get a signal whose magnitude will be scaled by x of -1. At the same time, it will be advanced by 1 unit. So I will get a signal like this. It is advanced by 1 unit. At the same time, it is multiplied by constant x of -1, where x of -1 is the scaling factor, nothing but a 1 in this case. So signal will be like this. And we call this as x of -1 h of n plus 1. Now second signal, if I apply to the system, which is linear time invariant, it will have the value like this with a magnitude x of 0. So now we are having a signal whose value is 2 at the instant n equal to 0, but actually it is x of 0 delta n. So this is passed through a LTI system. So what we'll have over here, so delta n will give a impulse response h of n like this, and this impulse response we need to just scale by x of 0, because here scaling factor is x of 0 and that is nothing but 2. So what we need to do, to the h of n we need to multiply with a 2, so that we will get signals like this. For n equal to -1, 1 is getting multiplied with a 2, so it's a 2. Then over here n equal to 0, I have a 1 getting multiplied with a 2, so this signal is also 2 for n equal to 0. And finally for n equal to 1, the signal value impulse response is -1 multiplied with a 2, so it is -2 like this. We'll get here a x of 0 multiplied by h of n. Let's go ahead to the third signal now, which is having the magnitude -1 at n equal to 1. Like this, but actually this is x of 1 into delta n minus 1. If I pass this through LTI system, where the scaling factor this time is x of 1, which is -1. So I need to multiply delta n by -1, but at the same time it should be delayed by 1. So h of n, impulse response is like this. I need to delay it by 1. At the same time, it need to be scaled by -1. So we will get a signal like this for 0, then for 1, and for 2 we will get signals. So it is delayed by 1 and multiplied by -1. We will get impulse response -1, -1, and -1 multiplied with the -1 is 1. So we'll get this as x of 1 h of n minus 1. So we'll get this impulse response. Now what we can do in the end, we can use the property of superposition because it's a linear system. So along with the scaling property, it also exhibits a property of superposition. So by the superposition property, which is inherently there because the system is linear one, what superposition property tells, if I sum of this, I will get x of n. So if I sum of this, obviously responses should also be summed up to get an output. So if I sum this up, I will get x of n like this. Exists from -1 to 1 and have the value 1 for -1 of n, then 2 for n equal to 0, and -1 for n equal to 1. So this is x of n. Meaning if I pass the sequence to the system which is linear time invariant, I should get output, and the output should be a summation. Now what we have to do, we have to sum this 3 because we have added this 3. So by the virtue of superposition property, I need to add this also. So let's find out what we will get if I add. So for doing addition, I will get the instance from -2 to at the instant -2, I'm having only a one signal present, that is 1. So for -2, this will be 1. For -1, 1 and 2 will get added to become 3. For n equal to 0, -1 added with 2 will give you 1, and 1 is added with -1 will give you 0. For n equal to 1, it is -2, here it is -1. So if I add, it will be -3. and in the end for n equal to 2, there is no signal over here, but here it is having a value 1. Meaning, if x of n is given to this LTI system, I will get the output which we consider as y of n. And to do this, I should know system impulse response. And that impulse response is nothing but h of n. So as far as this particular thing is concerned, I can sum this into a one formula, and that formula we derive, which call as a convolution sum. So the formula that we get over here is like this. To get a y of n, I have done a summation which will be from minus infinity to infinity, and over here I have the sequence x of k multiplied with h of n minus k. We can expand this and we'll verify whether this is compatible with the formula or not. So since I'm getting a y of n span from minus 2 to 2, so and k will have the sequence from minus 1 to 1, so I can say this y of n equals summation k ranging from minus 1 to 1 x of k multiplied by h of n minus k. Suppose I want y of minus 2. That means I put n equal to minus 2. I will get summation k equal to minus 1 to 1 x of k h of n minus n is minus 2, so it is n h of minus 2 minus k. And if I simplify, I will get x of minus 1 multiplication with h of minus 2 plus 1 plus x of 0 multiplication with h of minus 2 plus 0 plus x of 1 multiplication with h of minus 2 minus 1. So in the end, y of minus 2 is nothing but x of minus 1 multiplied by h of minus 1 plus x of 0 multiplied with h of minus 2 plus x of 1 multiplied with h of minus 3. So to get a y of minus 2, we have added this sequences, and to this sequence is obtained from this. So what I can say from here, x of minus 1, so the original sequence is over here, x of minus 1 is 1 and h of minus 1 is also equal to 1 in this case. So it is y of minus 2 equal to 1 multiplied with a 1 plus x of 0. X of 0 is 2 multiplied by h of minus 2. Unfortunately, we are not having h of minus 2 present because h of n exists from minus 1 to 1 only. So what I can say, h of minus 2 is 0. Similarly, even if x of 1 is present, which is minus 1, but h of minus 3 is not there, so it's 0. So in the end, y of minus 2 we obtain as 1. see here, y of minus 2 is 1. Likewise, we can verify. Let's verify for n equal to 1. So I want y of 1. So the formula will stand like this: k minus 1 to 1 x of k h of 1 minus k. If I expand, I will get this as x of minus 1 multiplied by h of 2 plus x of 0 multiplied by h of 1 plus x of 1 multiplied by h of 0. X of minus 1 is 1, h of 2 is not present only, x of 0 is 2 given, and h of 1 is minus 1. X of 1 is minus 1 and h of 0 is 1. So if we simplify, we will get y of 1 as minus 3. So from the formula we got y of 1 as minus 3, y of 1 as minus 3 from the graphical also. So what I can say that this particular thing, y of n is summation k from minus infinity to infinity x of k into h of n minus k is valid, and we call this as convolution sum. What is the advantage of this? So advantage is this: suppose in a system, yes, it is a linear time invariant system. If I know impulse response h of n of the system, impulse response is nothing but response given by system for an impulse function. To the system, you apply any input, you can get an output through a convolution, which is represented by y of n is x of n convolved with h of n. So this is a symbol for convolution, and the formula we have already discussed. So this is the most important part which we derive from a LTI system. Hence, linearity and time invariance of the system is the paramount of importance. And secondly, any function x of n can be represented by its shifted and timescale delta versions. Thank you.